Welcome back, everyone. In this video, we're going to continue learning about properties of gases. Specifically, we're going to discuss effusion and diffusion and using Graham's law to determine the molar mass of a gas sample if we're given information about the effusion or diffusion rates. So what are these processes? So if we look at gas particles, remember that they are going to expand to fill the shape and the size of their container. So let's imagine that we have gas particles that are in a box, and we cut a hole through a divider on one side of that box, and it allows the gas particles to go through that tiny hole to the other side of that box. We call that effusion. And an everyday example of this could be if the high pressure of gas inside your car tire escapes through a small hole because you've got a puncture. Diffusion describes the distribution of gas particles, multiple different kinds of gas particles throughout the open volume of space. So this is actually very frequent. So imagine that you are making a very delicious breakfast in your kitchen, and your roommate's in their room, and they smell the delicious aromas of your, waffles or pancakes or whatever it is that you're making. The way that the gas particles got to them was through diffusion. The gas particles left their source, which was the food that you were making, and diffused throughout the air to reach their nose. And so these two processes, while they are technically different, for our purposes in Chem 110, we're going to relate them simply to the, we can talk about the rates of effusion or diffusion kind of in the same terms. And so we as we saw earlier, that the speed of the gas particles is dependent upon the temperature and the molar mass. So we can compare the rates of effusion or diffusion using those same relationships. So we can talk about the rates of effusion and diffusion in terms of the root mean square speed of gas molecules. So if we take the rate of one gas and want to compare it to the rate of a second gas, we can calculate that ratio by calculating the ratio of the root mean square speeds. So all we've done here is taken the relationship between root mean square speed, the ideal gas constant R, the temperature in Kelvin, and then the molar mass in kilograms per mole, and we're taking a ratio. Because the number 3, because gas constant R, and the temperature will be the same since we're talking about the same conditions, we can simplify and eliminate those terms from this relationship. The algebra in this gets us then that the rate of gas 1 over gas 2 is equal to the square root of the molar mass of gas 2 over the molar mass of gas 1. Notice that the rates and the molar masses are inverted, as we would expect because of the relationship between molar mass and speed. This describes what we call Graham's law. And so we can use Graham's law to gather information about molecular speed or molar mass of a gas of an unknown by comparing it to a known. And as we've seen already, light molecules are going to go faster, effuse or diffuse faster than heavier molecules. All right, so try this problem. See if you can determine the order of these gas molecules in increasing rate of effusion. Pause the video and try this on your own. Welcome back. So, as we discussed already, light molecules are going to move faster and therefore effuse or diffuse faster than heavy molecules. So what we need to do here is apply Graham's law. We first want to determine the molar mass of each of these gas molecules. And then again, because we know an increasing rate means a decreasing mass, we can rank them. And so xenon's the heaviest, and ammonia is the lightest. Therefore, they will increase in rate, going from the heaviest molecule to the lightest molecule. Okay, here is another problem. Try to determine the identity of the gas using information about the effusion rate and the identity of the known. This one's a little bit more difficult, but I'm confident you can do it. Pause the video and try this on your own. Welcome back. So, applying Graham's law, we can relate the ratio of the rates to the ratio of the molar masses. We know the identity of one of the gases, but we don't actually know the rate. What we know is the ratio of the rate. We know that the unknown gas is effusing 1.49 times faster than chlorine. So we should expect that the unknown gas is going to be lighter than chlorine because it's effusing faster. For the purposes of this, let's say that the unknown gas is gas number 1 and gas number 2 is chlorine. It doesn't actually matter which one you say is which, so long as you can solve for it mathematically. So we know that the unknown gas is moving 1.49 times faster than chlorine, and we know the molar mass of chlorine. Therefore, we can rearrange and solve for the molar mass of the unknown gas, which is just under 32 grams per mole. When you look up the identities of, or the molar masses of each of these gases, we can see that this gas must be oxygen. That's it for this video. Thanks for watching. Have a wonderful day.